Hello, we're Nish, Caroline, and Lee, and we are B6, the AnywheRe augmented reality piano. So to start understand our problem, first we need to understand what music composition and arrangement is. It's when you take a piece like this and turn it into something like this. A piano, but people that do this for a cappella groups or for music composition on their own hobbies often find that they can't carry around a piano because it's not portable, they're expensive, and the things that are available online are simply not usable because you can only play one note at a time and you don't have the feel of a real piano where the harder you press a key, the louder you can hear it, and you find all those balances. And here you can see the outrageous prices of things that are available online. So we wanted to create a simple, cheap, portable solution that would help people have a portable piano that they can use on the go anywhere. So next I'm going to pass it to Lee to introduce our initial solution.
Our solution approach is demonstrated through this block diagram. On the left side, you see with the gloves, each one on the left and right hand would have a PCB that would have a STM32 microcontroller with a Bluetooth external module, as well as 5 pressure sensors that would go on each of the fingers. That would send data over to your phone, which would be mounted on a laptop at a 45-degree angle, which would look at a paper keyboard, each with colored markers to show the 4 distinct octaves. In addition to that, on the software side, you would have a mobile app with an Xcode wrapper that would go around the Kivi interface, which would essentially do all the processing for the OpenCV. And the mobile app Xcode wrapper was useful because you needed that for Apple iPhones, whereas Androids did not require that. That information would be sent to the speaker to then output the actual notes played.
We actually made a couple changes to our system diagram and design. So one of the main changes was instead of using an STM32 plus the HDO5 Bluetooth connection, we ended up changing our module to an Arduino Nano 33 BLE. This has the BLE module included in the Nano, and though it's a little bit bigger, it also is very simple to use, and all our microcontroller really needed to do was read 5 sensors and send that information over. So we thought that was a better option. We also realized we needed to have batteries and a battery holder to keep a wireless system. And we also have cotton finger wraps. And so that's basically just to attach the pressure sensors to the finger wrap so that they can actually be worn on your hand. Then on the phone and desktop side, we originally were just going to mount the phone to the desktop, but we realized that we actually wanted the camera to have an overhead view of the paper keyboard rather than a 30 to 45 degree angle so that the warping would be a little bit more consistent in the computer vision. So we're using an overhead stand to mount our camera, and our camera is our phone. So if your phone is overhead, you can't really see the interface on it at the same time as it's watching your hands. So that's why we moved to a desktop or laptop interface for our app on the user end. Also, because we have an overhead stand now, we can actually see all 4 octaves at the same time of the entire paper keyboard, so we didn't need to choose two octaves to be using. So those cover most of our changes. Itself works. Our app is run in Kivi so that we can run it natively on any desktop or laptop that wants to use the interface, and also because Kivi allows us to build our interface in Python and easily integrate our OpenCV, which is also written in Python, and utilize our Bleak Python package to connect to our Bluetooth. So on the left, we can see our glove sending pressure information over BLE and our video feed showing us the paper keyboard and where the gloves are on the paper keyboard. So in the app, that translates to when you open up the app, you'll have a glove connection stage. That's where Bleak Client is going to start an async program that will continually read the pressure characteristics at least at 30 hertz. Our gloves are actually sending at a rate of 10, one time per 10 milliseconds, but we don't need to read it that frequently because our CV really only updates at a minimum 30 frames per second, although we're currently running it at 60 frames per second. So in this stage, you can also choose to pair either your left or right glove or both of them at the same time, whatever you choose. Then you move on to the calibration stage, which will show you the paper keyboard, and you can select the red dots manually on the paper keyboard in order to warp the keyboard. This uses OpenCV to do the warping and the thresholding of the keys to figure out how many there are and where they are. And MediaPipe is used to figure out where your fingers are. And then you'll move on to the playing stage of the app, which just puts up a piano and colors the keys depending on the volume that you're playing them, using the information from the previous two stages.
This code here was used for interim demo and highlights the functionality of the computer vision subsystem of our project. The three main essential areas of the subsystem is contour detection, finger segmentation, and key identification. Starting off with contour detection, as I run the program here, we'll first show the image that we're inputting. This is what the test image looks like. You can see the red corner dots, which essentially are used to identify the location of the piano. Contour detection is the little green pixels there that are able to find that, get the centroid locations of it, and then with those coordinates, I can essentially create a homography matrix to then warp and zoom into the piano as such, like that. We'll then also apply a cropping and a gray border, and then also some image processing to go into key segmentation. Here we have thresholding there as well, and you can see the divisions between the keys through that image processing. Then here, this is the output after we apply segmentation. Basically, on the scale of 0 to 255, for all these given areas, we give it a pixel value to show that it's a distinct key. So it's labeled with that pixel value, essentially. Last section for key identification is relying on the MediaPipe package. And every time I show my hand, it loops through every joint in both my left and right hand and shows the coordinates of each fingertip on the screen. So I will show you here. Here are my fingertips in blue, and then you can also see the white dots on the bottom in what it thinks it is on our generated piano keyboard, all those pixel values. What it'll do is that it'll find the coordinate, then find its pixel value in the window below, and then reverse engineer that to find the label that we gave it. They're all going to be numbered for different sectors. You can see above here in the terminal, it even knows it's my right hand with the index, middle, ring, finger, coordinate value, and then given the actual sector number that distinctively identifies it from another key to another.
This is the glove for our project. This glove has 5 MD3060 force resistor sensors, an Arduino BLE, and a battery pack. The battery pack is connected to the proto board and powers the entire circuit in Arduino with 3.3 volts of power. The circuit itself consists of 5 10K ohm resistors that connect to the pressure sensors on the fingers. These pressure sensors are variable resistors that limit the amount of voltage that is able to flow through. As more pressure is applied, the more resistance there is, and according to Ohm's law, that means there is a higher voltage that is read. The voltage level is constantly read by the Arduino, as we can see here. This voltage level is thresholded into 4 separate categories: no volume, low volume, medium volume, and high volume. These thresholded values are then sent to the interface through Bluetooth as a Bluetooth characteristic. This characteristic has 8 bytes, and we use 5 of the bytes, each representing one pressure sensor volume level.
So here's our actual app interface. We're connecting our right and left glove here, and while that happens, we proceed to calibration. So here you can see the video stream, and we're gonna click capture image to actually take a photo so that we can now click on the screen and pick the red points to do our warp. So that's going on here, 1, 2, 3, 4. And now we can see the output image. This is just a bit of a check so that you can see your fingers are showing, and the output image is kind of what we want to see, which is that dark to light gradient going left to right. That's how you know that it's worked. And so we're going to proceed to the interface. So now we're going to show a full view. In this first segment, we're just playing a lot of the notes at once because we wanted to make sure we can play full chords that you can hear here. And next we're going to show off some of the volume control, so you can see lighter colors mean softer notes, and those are playing as you go along. Thank you.
All right, I'm good.
All right. It just